This is going to be the video over the solutions for the chapter 5, at least the quantitative problems that you'll run into. So I just wanted to give you a feel for what was going on. This is going to be the first question right here, and I'll show you what I did in order to be able to solve it. So we're going to consider an atom with a K-shell binding energy of 30 keV. The binding energy of the M-shell electron is 0.7. An electron with a kinetic energy of 25.3 keV is ejected from the M shell as an Auger electron following an L to K transition. So the binding energy of the L shell electron is what? Now, I do think I'm going to need to go here and do a little bit of editing here. That should go away. Okay. So what we have is a situation here where we have an atom. We have the first major shell here, then we've got the second, which is the L, and then we have the M, which is the third shell. Now, the K, the L, the M, we know that the binding energy here is 30. We know that the binding energy here is 0.7 keV. We don't know what the binding energy is here, so that's what we've got to find out. So we know that there's a jump of an electron from L to K to pardon me, to help fill that vacancy. When that happens, there's a certain amount of energy that's released. Now, we don't know what that energy is because we don't know what the difference of the binding energy here is. What we do know is that this photon comes out here, interacts with the M, an electron in the M shell, and it goes off. We know that it has an energy of 25.3. We also know that it took 0.7 keV to liberate it. So this photon here would be the sum of the 25.3 and the 0.7, so 26 keV. So we know that the 26 keV was carried out here. Some was used to liberate this from the M shell, and then this was the rest. Well, since that was 26, and we know that the K shell has a binding energy of 30, the question is, what is the difference here, or what is the binding energy here for this? And basically, it's going to be the difference here between the 30 and the 26 that was delivered. So it's going to be 30 minus the 26, and that should give you an answer of 4. So let's check that out. Let's see if that's actually the case. And that's the case. So that's the imagery behind solving that particular problem. Now, let's go on to number 2 here. You can see here, okay, the energy levels of the K, L, M, and N shells are in tungsten. Are these levels? Calculate the energies in keV of the characteristic X-rays that can result from transitions between the K and the L shells. The basic thing that you do here is you take this value, subtract this value from it, and you should come up with this, 58.6. And as you guys are going through and working the problems, as I was working this, I was finding a few mistakes. So you may have to go back and recheck some of your work here. Question 3. The question's turned around. What's the transition between K and M energy levels? So what's the energies of those characteristics? If we take K and we subtract this, then we should end up with 67.2. So that's where that value comes from. For number 4, what is the maximum kinetic energy in keV of electrons in an X-ray tube with a kilotube voltage, with a tube voltage of 120 kVp? The maximum energy is basically going to be the same as whatever this value is, but you slap a keV at the end of it. That's pretty much how you work that one. Number 5. Approximately what percentage of the kinetic energy is converted to photons as these electrons come to rest in the thick tungsten target? And the answer here is just going to be 1. It's a very inefficient process. So now we're getting on here into the more complicated questions. Question 7. What is the minimum wavelength of the Bremsstrahlung photons in nanometers in an X-ray tube with a tube voltage of 120 kVp? If you use this particular formula out of the book, it's 1.24 divided by the kVp, and that'll be in nanometers. So in this case, it's 1.24 divided by 120, so 0.010 nanometers. Problem 8. What is the approximate average energy of the photons in an X-ray tube with a tube voltage of 120 kVp? Basically, it's 1/3 of that. So you take whatever I would put here, you would take 1/3 of it, and that would end up being your answer. Question 9. The dose rate in free space of radiation therapy treatment beam is 267 centigrade per minute at a distance of 150 from the source. The dose rate in free space at a distance of 80 is going to be what? Well, you can figure here that since we're getting closer and closer to the beam, that we should end up with a greater dose rate. The question is, what do you do to calculate that? This is the inverse square law. This is what you're going to use. So we know we start at one particular point at 150 centimeters. It's going to be 267. We're moving to 80. We simply don't know what that intensity is. But we can take this formula and we can solve for that for the I2, and we can come up with basically I1 times this ratio squared, or 267 times 150 divided by 80 squared, and comes up to be 939 centigrade per minute. And this formula will end up producing that. So, question 10. The intensity of a linear accelerator radiation beam is 1 unit at a distance of 100 centigrade from the source of radiation. Use the rule of thumb to estimate the intensity at a distance of 110. Now, we know that the intensity is going to drop off because of the inverse square law. The question is, using the rule of thumb, how do we find that? Now, if you look, eventually, it's going to take a while. There we go. Sometimes it just takes a while for things to load up. So, rule of thumb, if the percentage change in distance from the source is small, the percentage change in the intensity of the radiation beam is approximately twice the percentage distance. So when we go here and using the rule of thumb here, we're going from 110 to 100. If we find a percentage here, that's a 10% change. The rule of thumb here is that it's going to end up being a 20% change. Now, since 110 is going to be further away than 100, it's going to be a reduction. So we get to reduce this by 20%. So 20% of 1 unit is going to be 0.2 units. We subtract that from 1, so we end up with 0.8 units. Let's see, which problem was that? That was 10. So, all right, so we're going on to 11. All right, the intensity of a linear accelerator beam is again 1 unit at a distance of 100 centimeters. Use the inverse square law to calculate the intensity at a distance of 110 to 2 decimal places. Here again, we're going to go back and use the inverse square law. You can follow the process here as we name what all of these are, and then you find out it's 0.83 units. So the rule of thumb, again, will get you close. This gets you a lot closer. So for number 12, The radiation emitted by Cobalt-60 has a half-value layer of 1.2 cm in lead. So what is the linear attenuation coefficient of lead for Cobalt-60 radiation units of basically whatever it is over the centimeter? So to find that, you can use this formula. The half-value layer is equal to the natural log of 2 divided by mu. Mu is equal to the natural log of 2 divided by the half-value layer. So you come up with 0.58 to the cm to the minus 1. Go on to 13. Radiation emitted here again is the half-value layer is 1.2 cm in lead. What is the average distance in cm that the Cobalt-60 photons travel in lead before interacting? So if you'll go through here, you'll find that basically what we're looking for is the mean free path. So the mean free path, or L, is going to be 1 over the linear attenuation coefficient, or mu is going to be equal to the natural log of 2 divided by the half-value layer. If you know all of that, you can splice it together and find out that the mean free path is the half-value layer divided by the natural log of 2, or 1.7 cm. Going on to question 14. Oops, there we go. The radiation emitted by Cobalt-60 has a half-value layer, again, of 1.2 cm in lead. If we have a 5 cm thick cast block that's fashioned from lead, what percentage of Cobalt-60 radiation will be transmitted through this block? And round to 1 decimal place. So we go through here, we find the intensity. We know what the half-value layer is. Once we know the half-value layer, we can determine what the linear attenuation coefficient is, which is this. The ratio of the intensities, which I believe is what it's looking for here, what percent will be transmitted. This ratio here is talking about what is transmitted. And when we take both sides here and divide it by I sub naught, this is going to be what's transmitted, or the percentage. So we take e to the minus linear attenuation coefficient and multiply it by 5 point, that should be 5.0 cm, and you come up with 0.0555762. If you take that as a percentage, you basically multiply it by 100, slap a percentage on it, and it becomes 5.6%. For problem 17, a measurement of the radiation level at a distance of 1 meter from a brachytherapy patient is 6.7 milliroentgens per hour. How many half-value layers of shielding material are necessary to reduce this to 2 milliroentgens per hour at 1 meter? Since the distance is the same, let's see, did I skip? I did skip. I'm sorry, I need to go back. I need to go back to number 15. That's my mistake. Apologize for that. The linear attenuation coefficient for a material used to construct compensators is this value. What percentage of the radiation from this beam is transmitted through 15 millimeters of the material? Since we know the linear attenuation coefficient, we know how far it's going through. In centimeters, remember it said 15 millimeters, but I changed that to centimeters because it has to match this unit in order for it to be able to cancel out. So the amount that's transmitted is going to be this computation, which ends up being 0.79, changed to a percentage of 79%. Question 16. What is the half-value layer in CM? Well, to find the half-value layer, we know that the amount that's transmitted is going to be 50%. So we know that this ratio is going to be 0.5. So we set it equal to 0.5. is our linear attenuation coefficient. We need to find the value of x. In order to find the value of x in an exponent, we take the logarithm, natural logarithm of both sides. When we do that, this expression here becomes a coefficient, and we have it multiplied with the natural log of e, which is 1. That's why this changes around this way. Solving for x gives us this expression, and I ended up with 4.5. I think the book has 6.5, and I think that may be a misprint. If anybody can find out if that is not a misprint, just let me know. For number 17, for real this time, measurement of the radiation level at a distance of 1 meter from brachytherapy patients, 6.7 millirangens per hour. How many half-value layers of shielding material are necessary to reduce this to 2? Well, here's how I went about doing it. I know the intensity at the beginning is 6.7. I know we want to reduce it to this. The question is, how do we go about doing that? Well, how many half-value layers is it going to take in order to produce this value? So how do we change 6.7 to 2.0? We're going to multiply it by 1/2. The question is how many times? Because once you start putting half-value layers in there, you're cutting the exposure down. In order to be able to solve this, I divide both sides by 6.7. Again, take the natural log of both sides. This becomes the coefficient. When I divide or isolate n by itself, I get the natural log of 2 divided by 6.7 divided by the natural log of 1/2, and I come up with 1.74. It's almost 1.8 as it is in the book, but I come up with 1.74. If we look at 18, I come up, there we go. Same process, but what it's trying to show you here is how far in meters would you have to move the patient in the absence of shielding to reduce it to that same amount. And it's trying to get you to link in your mind the connection between a half-value layer and moving a patient away. This obeys the inverse square law. So we know what we start with, we know what our distance is at that point. We know what we want our exposure to be, we just don't know how far away we have to move it. We use this particular formula, we solve for x, and you come up with 1.8, and that will be 1.8 meters. Moving on to 19. The mass attenuation coefficient for compact bone is this, for this photon energy. What percentage of photons are either absorbed or scattered by a slab of bone 4 cm thick? The density of compact bone is this. Now, the mass attenuation coefficient, if you've been doing your reading, the mass attenuation coefficient is the linear attenuation coefficient divided by the density. We do this in order to be able to take different forms of the same type of compound and then try to figure out, regardless of the density, how much will it attenuate a beam. So that is our mass attenuation coefficient. If we take the mass attenuation coefficient multiplied by the density, we come up with just the linear attenuation coefficient, which is what I've done here. So I come up with 0.969 to the over every cm per cm. I'll put it that way. I can then use the intensity equation and fill in what I know. I know that this is going through a 4 cm slab, so I can put that in there. I can also now put in the linear attenuation coefficient, and I can get the amount that's transmitted, which is 0.0207. If I'm looking for the amount that's attenuated, it's going to be 1 minus that. In other words, what's been stopped or what's been deflected. The amount that's attenuated is 1 minus this, and I come up with 0.9793 or 97.9%. Going on to question 20. Narrow beam attenuation of an X-ray beam by 0.5 millimeter thick lead foil is 91%. So what percentage of the radiation will be attenuated by a 1 millimeter thick lead foil? So if we go to the problem here, we know that the attenuation is going to be 0.91. So 91% of the beam is attenuated. That means the amount that's transmitted is actually going to be 0.09. When we use this particular formula, rearrange it here, we know what the amount of transmission is. We can fill that in. That's going to be equal to the minus mu times 0.5 millimeters. We then take the natural log of both sides. Again, this stuff here, this exponent becomes a coefficient. The natural log of e disappears. So we end up with mu being equal to the natural log of 0.09 divided by minus 0.5 millimeters. And we come up with 4.816 per millimeter. So the amount here that is transmitted is going to be this. And up here, we have that going through 1 millimeter. So the amount transmitted is going to be 0.0081. The amount that is attenuated is going to be 1 minus that. And we come up with 0.9919 or 99.2%. For 22, it's basically the same problem as 21. It's just it's changed from 1 millimeter to 1/4 of a millimeter. We can use the same basic information regarding the linear attenuation coefficient that we had of number 20. All we do is we plug in 0.25 millimeters. We come up with this. This is the amount that's transmitted. The amount that's attenuated is 1 minus that, 0.7 or 70%. I think you'd have to type in 70.0% because it says around 1 decimal place. So that is a quick overview of the mathematics behind these particular problems in Chapter 5.